Okay, well, welcome everybody to the third and final masterclass session in this series. I hope you've been able to join the previous two sessions, but I'm delighted that we will close off this session with a focus on climate. So the masterclass series is something we've been running at the Royal Met Society in conjunction with the University of Reading Met Department now for about 3 and a bit years. We have a series that tends to run in the spring, and then this series that runs in the autumn time as well. The aim is really to take areas of the science and bring you as attendees of this session up to date with particular areas, and an opportunity to ask questions of various speakers and responders that are on the call. I've got a few slides to go through before I hand over to Hilary, who's going to introduce our speaker for this afternoon. So this session is on winter storms and European Atlantic climate. And as I say, it's the third one in our series for this masterclass session. So we're on Zoom. Just some pointers for you, those of you who haven't joined the masterclass series so far. So we have enabled closed captions. So if you want to see the text coming through from this, please do click on the closed caption tab at the bottom of the screen. And there'll be about half an hour towards the end of the session for questions and answers. So please do put your questions in the Q&A, and we'll get through as many of those questions as we can before we have to close off. If you've got questions for Chris as the speaker or Nigel as our responder, either please just put them in the Q&A, that would be great. And just to let you know that we are recording the masterclass, and this will be available for members of the Royal Met Society after the event. So membership, I guess, let's move on to that. We're a membership organisation, and many of you will be members already of the Royal Met Society, but there's some information here about the benefits of being a member of the Society. And at the top of this slide, you can see a web link and an email address if you want to find out more. We also run professional accreditation in meteorology, so the registered and chartered meteorologists, and there's some details of both of these on the slide as well. And at the top of this slide, again, a web link and an email address if you wanted to find out more. And again, there'll be people on this session listening in who are already registered or chartered meteorologists. I just encourage you to take a look at that and find out more. Hilary will be introducing our speaker for this afternoon, Chris, and I will introduce Nigel after Chris has spoken, and then, as I say, we'll get both of them involved in the Q&A towards the end of this session. And I just wanted to highlight two meetings that the Royal Met Society is running, one at the end of this month on the 30th of November. This is a virtual meeting looking at seasonal forecasting, an overview of what seasonal forecasting is, how it's advanced over recent years, and the limitations, I guess, that we still have with seasonal forecasting, and also taking a look at this winter's seasonal forecast, which I guess all eyes are on the winter forecast as we have to kind of grapple with temperatures over the winter and the energy crisis that we're in. So that's a virtual meeting. Please feel free to register if you want to join us for that meeting on the 30th of November. The second meeting is at ECMWF, so this is an in-person meeting, and that takes place in December, on the 7th of December, and this one is on challenging forecasts and difficult decisions. So it's looking at how we predict the likelihood of severe weather events. And as I say, that takes place at ECMWF. It's badged as our Christmas meeting, so do come along if you want to join us for that. Okay, so I'll hand over to Hilary. Ooh. I can move on my slides.
Thank you very much, Liz. I'm very pleased to be able to say a few words about meteorology at the University of Reading. We are predominantly a research organisation, and we do international leading research on weather and climate, all aspects of weather and climate, but we also have a very active teaching programme. We have undergraduate degrees and MSc programmes and PhD programmes, full and part-time. There's a new MSc programme, Climate Change and Artificial Intelligence, which started this year. We are also offering online courses, which may be of more interest to some of the audience here. There's two kinds. There are free introductory online courses, quite short courses. On some of them are on the Future Learn platform on understanding the weather, data assimilation, which is not a mathematical course, and one's on climate change and climate intelligence. We're also offering more advanced online courses which run over the course of a term on fundamentals of meteorology, climate services and climate impacts, statistics for weather and climate, and tropical meteorology. These are at a cost of £500, discounted to £450 for Royal Met Soc members. All the details of those are on our website. And of course, there are these masterclasses. I'm now very pleased to be able to introduce Chris O'Reilly, who's going to talk about European climate variability. Chris did a PhD at Imperial College, and then he's done a postdoc in Japan. His work has focused on the intersection between decadal predictions and climate predictions, and also on air-sea interactions, and how the sea surface temperature influences storm tracks in the mid-latitudes, and also some work on tropical variability. So Chris, over to you.
Okay, thanks, Hilary. That's very kind of you. I've unmuted myself, and I just needed to share the screen. And there we go. Thumbs up. Is that good?
Yes, that's come across.
Great. Okay. We quickly move all of these screens out of the way. I get all sorts of screens here. Don't need to see anybody there. Okay, thanks very much. So yeah, so it's nice to be able to give this talk today. I think it's a bit different than a normal kind of research talk that we tend to give. So I'm hoping that it's going to be of interest to those of you listening in, and those of you listening in the future online, as this has been recorded. So I'm going to try to give an overview today of European climate projections in general, and some of the underlying variability and uncertainty in these climate projections, and where they sort of arise from, and maybe touch on, and towards the end I'll touch on some of the kind of the biggest challenges that we have in kind of in effectively being like using these projections operationally. So, you know, this climate science has kind of gone from being something that's theoretical, thinking about climate change, to actually now there's more demand for actually predicting exactly what's going to happen. So those are some of the aspects I'm going to try and touch on in this talk. If I go, I can click through, great. So this is just an outline of what I'm going to talk about. The first is this outline, and the second is I'm going to talk about some observations of past European climate. So what the evolution we've seen in recent years and over the past century. I'll then talk about coupled model projections of European climate and a bit of what goes into these. And then I'll do an overview of some of the sources of uncertainty in these climate projections, and how we think they perform, where we think they have some deficiencies potentially. And finally, I'll touch on actually using observational constraints to adjust these climate projections. So there's increasing amounts of work on trying to take the projections that are made using coupled climate models and actually change them. So actually realize that we know that they're deficient in some areas, and how can we possibly change them to improve the projections that we make, and actually that people are actually now using, right? People making adaptation decisions based on climate projections. So it becomes kind of an operational problem. We want them to be as good as possible. And then finally, I will give a summary and repeat some of the things that I've said, and yeah, hopefully highlight some interesting points. Okay, so let's kick on. So the first thing that is really obvious if you look at observations of past European climate is that it's not that much different than global climate in some respects, particularly when it comes to temperature changes. This is showing, these two plots are showing the temperature anomalies in terms of an annual mean, so averaged over the whole year, and the left is the global surface. So obviously we've seen quite distinct warming since the 60s and over the whole 20th century really, but particularly accelerated warming since the kind of 60s and 70s. And that's matched in European land temperatures, but crucially it's much larger over land. Now this is a known property of climate change and global warming, But I think it's still, I think they're still remarkable that, you know, we constantly talk about 1.5 degrees, 2 degrees. These are global surface temperatures. Actually, what we've experienced is already above that, you know, in terms of European land temperatures. So so climate change isn't a future problem. It's already with us. This is something that we're now experiencing, and actually the rate of change is kind of over the past few centuries is basically twice as large as the global surface. So that's in terms of precipitation. I thought this was an interesting map that I found from the European Environment Agency, just showing that the annual temperature trends that are positive everywhere in Europe. Of course, there is some change in the magnitude of these things, but it's pretty universal. I mean, I thought the blandness of this map was interesting to me. So this is just making the point that it's all areas of Europe are getting warmer under climate change over the past 6 decades, and it's not just an annual thing. This is happening in all the seasons. So these are time series of UK temperature split up into different seasons. So they've just been offset here to give you an idea about the different seasons, and it's remarkable that the temperature changes generally are quite consistent across seasons, even though the variability is very different. So you can see the winter here is at the top, and the interannual variability in winter is much larger, say, than in the summer, where the force signal is a bit clearer. And I think that's also borne out in kind of lived experience as well. Like we all can remember probably some cold winters in our relatively recent past, but in terms of like really hot summers, I think it's really clear that we've been living through much warmer summers in the UK over the past decade or so. But yeah, the point here was just to make that the interannual variability in winter is much larger. So there's much more variance in winter than summer, even though the long-term trends and variability are quite similar. If we look at precipitation now, I think this is where things are probably a bit more interesting. Over the past 50 odd years, so these are trends from 1960 to 2015 here. We generally see on the annual average that there are wetter conditions over most of Northern Europe. Now, they're not all statistically significant. The dots here are some measure of significance. But we also see a drying in the Mediterranean region, so in the south of Europe. And this is for the annual mean on the left. And if you just look at summer, it's kind of different. So particularly over mainland Europe, where we tend to see slight drying in terms of precipitation in the summer. Now, this is important to remember when I show some of the projections, because these are these maps, in terms of the left map being maybe more representing the wintertime variability and trends, and the right representing the summertime trends. These are important to remember because these also correlate with the largely reflect the signals we see in the forced response in climate projections. So just important to remember this kind of rough pattern here, particularly in the winter, with this wettening in Northern Europe and Central Europe and drying in the Mediterranean region. Okay, so it's not just in terms of mean precipitation that these things are changing there. We also see change in extreme events. Now, I'm not going to talk about these much in this talk. Of course, they're a very important topic, and I don't want to seem like seem myopic in my focus here. But I'm really thinking about kind of longer term trends in seasonally averaged values. But just to make the point that these largely co-vary with extreme events. So when we get wetter, for example, wetter winters in Northern Europe, these are generally associated with also more intense precipitation as well. So this is a map of the observed trends in the maximum 5-day precipitation occurrence. So basically average up precipitation over 5 days and where it's maximum in summer and winter for each year, and then take a trend. And we can see that generally we're getting more of these events are getting stronger in Northern Europe, but also over most of Europe in both winter and summer. Okay, so now I want to talk a bit about coupled model projections. So that was just thinking about what we've kind of observed in the recent past. But before we kind of go into what the projections are, it's probably useful to think about where these even come from. So how we do this. It's easy to look at observations, right? Well, it's not easy to get them, obviously, but it's, once we have them, it's easy to analyze observations and see what the changes we've observed are. But obviously making projections of the future is really difficult. And to do this, well, I've got a first bullet point here is super obvious. I know climate projections are produced using climate models. But I think that's important to remember, that the projections that I'm going to show you are produced using climate models, which are basically weather forecasting models, the same general circulation models that are used to predict the weather, but with lots of added complexities. So, for example, obviously now weather forecast models are all coupled. It didn't always used to be the case, actually, but so in a climate model, they're generally an atmospheric model that's coupled to an active ocean model, and land models, and also consists of some kind of physics schemes that will have, for example, some kind of parameterization of clouds, which interact with incoming solar radiation. And then we also have things like trying to represent the physics between the impact of CO2 and then other aerosols. Effectively, if I'm not doing a very good job of explaining this, is because they are immensely complicated. These are things that run on supercomputers, take a long time to run, they're very expensive to run. And I guess the idea of them is that they reflect the best that we can simulate the climate system as we know it. Well, not as we know it, but as we can best simulate it. This is the idea anyway with running enormous coupled models like this. Now, of course, we approximate the physics in the same way that in an atmosphere model, we discretize the globe into regions, or into, if it's a grid point model, or if it's a spectral model, we reduce the number of the spectral resolution of the model, and we approximate it as best we can, so that we can actually run these things, and to produce actual climate projections with these, they're normally what you do is you change, for example, you prescribe emissions of different gases. So, for example, CO2 is obviously the main driver of climate change, but then also there'll be other aerosols that are included in this, and things like volcanic eruptions are in there and things. So you apply all these things to your coupled climate model, and then you run it forward. But I guess the crucial distinction to make with, I tried to draw the analogy with weather forecasting models. The crucial thing with these models is that they're free running. They're initialized at some point in the distant past, but they're essentially freely evolving. So the only things that you are changing is the forcing from things like CO2, and that's where obviously you're hoping most of the signal comes from. But whilst you're also simulating as much of the dynamics, if you like, and the interactions between the ocean and the atmosphere as you can. So that's probably quite a speedy overview of how you kind of go about producing these climate projections, is basically running these models, and to actually make useful projections of the future. Typically what's done in these large international collaborative projects, which I'll talk about in a second, is that you look at different future emission scenarios. So obviously we don't know what CO2 emissions are going to be over the next century. I mean, to be honest, we don't know what they're going to be 10 years from now, really. So what people have done is they've designed future emission scenarios that are approximately match what we think could happen, but they're not so numerous that we can't run them. So here's an example from an old paper where it shows 3 different emission scenarios. And the reason I've chosen this is to make the point that each of these individual lines is one model simulation. So one integration of the model, which is freely evolving and is running forward in time, and the temperatures are evolving. This is for global temperatures are evolving in each of these models. And the blue ones are all the same scenario. Now, these kind of simulations are run by institutions around the world. So these are international there's international focus on these things. In the UK, the Met Office obviously does lots of this. And I wanted to just make the point that these are then used to produce multi-model ensembles. So some of you will probably be familiar with weather forecasting model ensembles. And weather forecasting model ensembles are really powerful because the uncertainty, the spread in the ensemble, if you like, that reflects uncertainty in the response to the initial conditions. So the uncertainty is that weather's essentially chaotic. You get some signal from the initial conditions, and then as they run forward, the forecasts disperse, and that gives you some measure of uncertainty. The same is true to a certain extent with coupled models, but instead of just sampling kind of the internal chaotic variability of the climate system, each of these models, because they're different models, they also exhibit a different forced response. So when these kind of multi-model ensembles are used, they can't be used quite as cleanly in a probabilistic way as you would say with a weather forecast model. So that provides its own challenge, and I'll talk about that shortly in a bit more detail. Now, all these scenarios that I mentioned about running, here's an example of the most recent of these in this figure, and climate model production's been coordinated through something called the Coupled Model Into Comparison project. So there's been several phases of these, and the idea of these is they feed into the IPCC to make their assessment report on climate change and projections for the future. There's been these are three recent projects. So CMIP3 was an older project in 2005, then CMIP5, and then most recently CMIP6. And essentially each of the models that have been submitted to this effectively have been run by different groups around the world, but following defined experiments. So here's what's shown in the plot here is a different emission scenarios, going from red, which is the worst basically emission scenario. This is very strong future forcing, and which we don't think is now hopefully not so plausible or realistic, but anyway, going down to basically a much lower scenario where I think we cut off or start reducing emissions well, probably yesterday. Anyway, so these are different scenarios, and the point is that each of these groups that contributes to this runs their model or several versions of their model for each of these different forcing scenarios, and then when we combine them, we can come up with some plots like this that show some of the model uncertainty or internal variability as well but mostly model uncertainty to a given forcing scenario. So what's shown here is in the lines of the ensemble mean across all these different models, but the shading gives you some feel for even across those models what the different responses are to a given forcing. So these are all the same kind of effective emission scenarios in each or concentrations in each model. Okay, so that's kind of what I wanted to say about that, really. So when we look at these simulations over Europe and look at the projected changes, these are some of the results that we get. So this is from a recent paper by some colleagues at the Met Office, and shown here are the multi-model temperature changes in different European regions. So NEU is Northern Europe, that includes the UK still, and there's Central Europe, and then Mediterranean is Med. I guess that's obvious, but it's worth pointing out. And the top row here is for summer temperature changes, and the bottom is for winter. Now, just don't, the red and blue are two different model generations. So the red is the older models and the blue is the newer models, but you can see that they're more or less, whilst there are clear differences, they're more or less predicting the same sign of the signal, right? Obviously, for the mid-21st century, that we're predicting warmer conditions in both summer and winter over all these European regions, and also by the end of the century. Although by the end of the century, you'll see that in these different model models, model groups and model generations, the CMIP6 is the newer model generation, and CMIP5 are the older models. You can see that there is some difference in their projected changes, but they're all obviously all projecting warming. And I should say this is for the strongest forcing scenario. I'll say a bit more about these different scenarios maybe shortly. If you look at precipitation, this is where the picture is a bit more interesting. In the summer, most of the regions are predicted drying, but it's not universal. Some of the models are predicting wetter conditions, particularly the case for CMIP5 and maybe CMIP6. You can see the uncertainty has narrowed. That's the green lines here, but mostly drying in the summer in all these European regions. And the winter is also quite interesting. We generally actually, the models are projecting wetter conditions in the mid-century and by the end of the 21st century under this scenario in Northern Europe and Central Europe. But in the Mediterranean region, that's where there's projected drying. And that is consistent with the observations that we've kind of already seen emerging in the observations, but it's not I guess not very statistically clear in the observations we've got so far. So but the drying Mediterranean does seem to be a quite robust feature of the models in the winter. Now I think that's important, particularly for the Mediterranean regions, because obviously they don't really doesn't really rain in lots of these countries in the Mediterranean in the summer. So the winter is where water sources are replenished. So that's an important projection. These models also have changes in the large-scale circulation and storm tracks that are contributing to these things. So, of course, in the same way that storms are responsible for lots of our weather, the amount of storms we get are responsible for our sort of longer-term climate conditions, if you like. So what's shown on this plot is the change in storm track, changes in the storm track on the left and the jet stream on the right for across the three most recent generations of models. And this is from a really nice paper by Ben Harvey and other colleagues at the University of Reading. So you can see that the thing I liked about this plot is that actually, if you squint, they're kind of consistent. So I think, whilst I think the modeling has got better, I think it's interesting to note that they're projecting a lot of the same features. And now some of these are quite well understood physically, so we think we can kind of understand some of these things. But if just thinking specifically about Europe here, you can see that in the winter, the storm track's generally shifting slightly to the south and extending into Europe. So you can see that the mean storm track is shown in contours, and I think this is a measure of sea level pressure variance. So basically high pass variance. So basically the idea is when you get a cyclone coming in, that shows up in more sea level pressure variance. And you can, if I lose my mouse, so you get more storms. The storm track shifted slightly south in CM6 and in the other models, and it extends into Europe. And that's consistent with this, with the changes in the upper level jet. So the jets shifted slightly south, but also extending into, strengthening into Europe in the winter. Okay, I just sort of said that. So the southward shift of the storm track and the extension increases the rainfall in this kind of central northern Europe in the projections, or at least contributes to it. It's not obviously some of the changes in precipitation are you would expect purely on thermodynamical grounds. The idea that basically warming the atmosphere increases the amount of moisture being held, so we would expect generally more precipitation. But the extension of the storm track into Europe is also contributing to that. And I also got the same plot for summer because I think it's interesting and it shows quite different things actually. So again, the interesting thing about summer is that the storm track tends to weaken, and this is associated with a weakening of the equator to pole temperature gradient. So the storm track tends to weaken, and this is a robust feature of all of these climate models. This is an end of century projection, I should say here. But interestingly, that in the most recent models, it's quite clear that the poleward jet shift over the North Atlantic. So here you can see the mean jet is over, kind of pointing at the UK, if you like. But but it's strengthening to the north and then weakening in the core of the jet. So this represents a poleward jet shift in the future in these climate model projections. So effectively, this is less moisture is arriving in Central Europe. So this is less storms and less moisture is being advected over Europe from the upstream ocean, if you like, where we get lots of moist air. So, but effectively, this is contributing to the drying that we saw in this previous panel during the summer over Europe. Yeah, so that's a weakening of the storm track and will reduce precipitation during the summer. So there are these kind of clear signals, and we think we can understand some of the features that we see. But there are also lots of uncertainty in these climate projections, and some of these stem from, well, I guess most of them stem from the fact that we're trying to model a really complex process, really complex system in the future. We know that these models are imperfect. We know they've got deficiencies. So it's useful to think about what some of these sources of uncertainty are, to think about how we deal with these kinds of projections. So for the next section, I'm just going to talk a bit about some of these sources of uncertainty, maybe 5 minutes or so. And then, yeah, so I'll talk about some of the sources of uncertainty in these climate projections, particularly for Europe. So I've already mentioned this in terms of outlining what these CMIP coupled model intercomparison projects are and all the models that go into them. But it's important to note that scenario uncertainty is clearly a huge uncertainty in climate projections. And by scenario uncertainty, I just mean future emissions. So the amount of CO2 that we're going to emit over, well, from now until we stop emitting CO2 is going to have, that's the leading order forcing on future climate, and not just on global scales, but also on regional scales, as I'll show you in a second. But on global scales, it's really the only show in town. It's interesting. What's shown here is on the left is global surface temperature change from the most recent CMIP6 models under these different scenarios. So you can see the red scenarios obviously have where we have more CO2 emissions are warming more. But the reason I really want to show this figure, because I really liked it, is that this shows CMIP5 models on the right, and they flip this round so that we can get some idea about the end of the century, what the difference is between these older CMIP5 models and the newer CMIP6 models. And you can see that the CMIP6 models are generally for similar scenarios. Now, these aren't the same scenarios, but for similar scenarios of future emissions, you can see that they're generally warmer for these most recent models. And this is something that's I guess I don't know if it's a problem with models, but this is a big issue in climate projections at the moment, is understanding some of this uncertainty. And basically these models are showing a higher climate sensitivity, and by that I mean they're showing a stronger warming response to a given CO2 forcing. Now, there are formal ways of defining that, but that, for the purposes of this talk, I mean, it's enough to know that for a given forcing, the current models compared to the CMIP6 models are showing higher sensitivity than the previous models. So that's certainly a concern and something to understand, and also a big source of uncertainty, right? So know exactly what this kind of warming response is on a global level to increase CO2 is obviously a very important. It's obviously very important also on regional scales, talking about summer here. Okay, so not just so while scenario uncertainty is important, there are also other types of uncertainty, and actually these become more important when we look at regional scales. So this is from a really nice paper by Lehner et al., which is effectively an update of a Hawkins and Sutton paper where they first tried to do this. And And what's shown on the left is the warming response of a particular model. And what they did is they tried to calculate the fractional contribution to the total uncertainty of the climate projection. So, and the top row here is for global surface temperature, and the bottom row is for UK temperatures. Now, if you look at global surface temperatures, you see that very quickly scenario uncertainty, that's green here, completely swamps anything else. So by the mid 21st century, how much CO2 we emit, or we've emitted since kind of 2014, I think, completely dominates the uncertainty. Whereas if you go to UK scales, so the scales of regions in UK, or maybe I suppose Europe as well. So as you go to smaller scales, contributions from internal variability, which is shown here in orange, and which is obviously large initially in the early years, and potential method bias. So what that means is the model response bias. So the model uncertainty, effectively, that we don't know exactly how much the model will warm. That also tends to dominate. That also tends to become more important on regional scales. So there's a really interesting thing here where as we go to regional scales, making climate projections, we need to understand more about internal variability, but also model uncertainty. So these are the two things that I think we really need to understand lots about if you want to know about uncertainty in climate projections, particularly when we talk about regional scales. And one of the big contributors to uncertainty is large-scale circulation variability. So when I showed all those plots before about with different amounts of internal variability, lots of that is just random, basically noise coming from weather. And if we look at something like the evolution of winter circulation over the North Atlantic region, it tends to be dominated by something called the North Atlantic Oscillation. That's shown here on the right. This is the pattern. This is the leading mode of variability. It dominates the kind of year-to-year variability over the North Atlantic in the winter. And the interesting thing you notice is that it shows this quite distinct kind of decadal variability with this kind of weakening of the North Atlantic Oscillation, and then actually this really strong trend from the 60s to the 90s, which was a really interesting event, and actually had really big climate impacts if we look at some of the data. So this is highlighted just here below. This is just to make the point that as we go to regional scales, these kind of things tend to matter. Now, of course, for global temperatures, where you're effectively moving the heat around doesn't make so much difference in terms of this large scale circulation. But when we're talking about smaller regions like Europe, for example, these things make an enormous difference. I just want to bring your attention to this trend from the 60s through to the 90s here, where there was a real warming across most of Eurasia that was associated with this strengthening of the NAO in this region. So we got this low pressure bringing more, advecting more warm air from upstream, basically warming the most of the Eurasian continent. And that's what we saw here during this region. And then since the 90s, there's been this kind of cooling trend over most of Eurasia. At least there was from like the mid 90s to the kind of the early 2010s. So this is just to make the point that there are strong multi-decadal trends that are associated with this large-scale circulation variability. And actually, these make a big impact if you just look at climate evolution of temperature and precipitation in these regions. This trend, for example, from the 60s to the 90s, had an enormous impact on Mediterranean precipitation. For example, there was really dry conditions, and the prolonged 1990s Liberian drought that was associated with this. Now, that's all well and good, but that's looking at the past. I guess the point I wanted to make here is that this is actually not really well represented in climate models. So, excuse me. So if we look at the observed decadal circulation variability of, say, the North Atlantic Oscillation Index, we find that actually that's not well captured in coupled climate models. What's shown here on the left is all these grey lines are all the different kind of climate model runs that are used to make projections. And we see that these kind of this strong trend that we saw in the 60s to 90s almost never occurs in these models. So it's really at the outskirts of this model. So it's some hint that these are not being well captured by the coupled climate models that we're using to make these projections. And this does have implications for future circulation trends and the associated climate impact. The fact that this potentially not being well represented in European projections. And that's particularly the case if we think it's internal variability, it's important, but if there's potentially forced signals that we're not picking up, that has, again, even more drastic kind of implications for our projections. I just wanted to kind of draw a parallel with the weak circulation variability we see in initialized forecasts, because I think it's probably a related problem here. In initialized forecasts, they actually show skillful but very weak predictive signals, say for in decadal hindcasts of the North Atlantic Oscillation, which is basically the winds and large-scale circulation over the North Atlantic, and in seasonal hindcasts of the North Atlantic Oscillation. These both have this problem where there's these very weak circulation signals in these model ensembles, and this has been dubbed the signal-to-noise paradox. Yeah, I'll definitely be going to the Royal MetSoc talk by Adam Scaife, thinking about seasonal forecasts, because I think this is a related problem to the weak circulation variability we see on decadal timescales in climate models. The idea here is basically that the model's better at predicting the real world than it is itself, so it's not capturing this signal in the observations. When you average across the models, you get very weak signals. So I think this is a potentially related problem, and there are a number of factors that are probably affecting this. I'm not going to go into too much detail here. This is just a nice schematic that I made, so I thought I should show you it, of things that are potentially contributing to this. So we know the models are deficient, so we know there are jet biases and anomalies, but also we know that there are deficiencies in the ocean atmosphere coupling. The models that we're using are not resolving, for example, very sharp gradients in the ocean temperatures, and not well resolving kind of some of the key features in the ocean, but also in the atmosphere itself, because the models are not as high resolution as maybe we'd like them to be, and maybe there are other physics that we're not capturing well. Some of these feedbacks of synoptic eddies onto the large scale flow are not well represented. So those are three things that I think, amongst probably others, loads of other things, the three things that I think are possibly contributing to this. Okay, so now I want to move on to, after having talked about some of these sources of uncertainty, I want to talk about some kind of more recent research, and this is going to be, I guess, slightly myopic. Some of this focuses on work that I've been involved in. So just to be clear, before I go into it too much, there's lots of other work going on in this area, of course, but is the idea of making applying observational constraints to kind of, if we can, make projections better and improve them, and more valuable. I think, how are we doing for time? I think I'm doing okay. Just before I go on to discuss kind of some more of these regional constraints, just want to make clear that this is kind of an ongoing, this is a thing that's currently being used actively. So observational constraints, the idea is that you compare the projections of the models when they run over the historical period to the historical evolution of the climate in various ways. And by comparing each of the models to how they compare with observations, you can adjust them. So maybe you might downweight them, you might chuck them out, you might choose the ones that perform best. And it's something that's actively done. So for example, this is an example of that on the global scale. And these were used in the recent IPCC sixth assessment report. On the left, it shows the global mean change. I think this is at the end of the century, under different scenarios compared to a recent historical period. And you can see the unconstrained CMIP6 models have got quite a strong warming, particularly by the end of the century. But this is reduced substantially when these kind of observational constraints are applied. So the idea is that, and these are different algorithms, I'm familiar with at least two of these. The idea here is that you kind of weight the models based on how well they capture some of the observed variability. And by applying this, you change the projected changes. So it's something that's being actively used, and I think it's potentially an important way forward to provide better climate projections. So but this is for global temperatures. So this has also been done for European projections, and also have the same impact actually of slightly down weighting some of the projected warming. So this is a figure from a recent project that I was involved in, where lots of different groups came together and applied multiple different of these observational constraints to European projections. So this is showing for a Central Europe region here. And there are all these models, all these different methods here. And we're looking at the mid-century temperature change here. And by applying these, I'm not going to get into details of all these different methods. They're far too complicated anyway, and I don't have enough time. But the gist is the same. Basically, you're making some adjustment to an unconstrained model projection based on how it compares with recent observational evolution, and they differ in methods. It might be, some of them are based on, for example, comparing biases. Some of them are based on comparing some kind of recent trends. Some of them are also based on kind of understanding how different the models are to one another and making a weighting based on that. So there's all sorts of things going into this. But the point is that we can apply these, but it's very difficult to know how effective they are. So some work that we did to do this was to compare these constraints in an out of sample test. So the idea here was to take the raw unconstrained projection, which is shown in grey here, compare it to some kind of observations taken from a different model that was not used to make the projections itself, so kind of an out of sample model, apply the observational constraint, and then compare how well this constraint did to the unconstrained projection. So the idea is that when we apply this constraint to these different constraints to this out of sample model, we can actually verify it and see how well it did. And the long and short of this example has been cherry picked here, but the long and short of it is that you can improve projections by applying these constraints for these regions, but only for temperatures. So in all these methods that we tried, listed A, B, C, D, E here very imaginatively, what we found is that we could reduce the error. So this is a plot here of error in the projections in the unconstrained and constrained projections. So after we've constrained these projections, is in dark colors here, and the error is reduced for temperatures. So in summer, this is, for example, but in precipitation, it really didn't reduce the errors at all. Now, and this is only for a mid-century period, and I think this is maybe clear as to why, in at least in retrospect, because in the temperatures we have quite a clear forced signal already emerging from the noise in the observations. So when we apply our constraint, there is some signal for these constraints to pick up on. However they're applied, they're picking up effectively a warming signal in the temperature. But in precipitation, the trends are not so clear yet in the observations. So the methods are not working well. So I think this is a really interesting result, because it shows that basically we need to do a lot more to understand how exactly precipitation changes are going to manifest in these climate projections. So I think this is one interesting piece of work. I just wanted to highlight some other interesting kind of area, some interesting work going on in this area of observational constraints. This is an idea of constraining slowly varying ocean variability, and this is led by Daniel. This is some work by Daniel Beffert, who was at the University of Oxford. And the idea here is that to take initialized decadal predictions that can skillfully predict ocean evolution, but they're only run for 10 years. So decadal predictions are only run for 10 years. So in this work, what they did was basically take these climate projections and constrain them using these decadal predictions that are basically that have got some initialization skill. So you take this soup of uninitialized projections, choose those that are best represented by that most closely match the decadal prediction, should I say? And then when you do this, what you find is that actually you can reduce the error compared to the uninitialized predictions. So there's a sense here that potentially this kind of clever treatment of constraining model runs based on kind of initialized predictions is potentially a way forwards to constraining projections. Now, I should say this was only for the North Atlantic sea surface temperatures, so where we know the ocean exhibits low frequency variability. So this is kind of a test case, but there's some hint here that maybe this is a promising way forward. Yeah, some other work I wanted to highlight was a recent study that I led where we tried to estimate the impact of this weak circulation variability in the extratropical North Atlantic on the uncertainty in future changes in European climate by basically post-processing these projections, assuming that they are not getting these large-scale decadal modes of variability right, and effectively adding in the noise associated with this. And what we found is that the uncertainty in these mid-century climate projections over Europe was pretty substantial, substantially different when you added in this variability associated with the leading modes of variability. So the North Atlantic oscillation is one, but there was several going into this, and I can maybe say more about this afterwards. I just wanted to highlight that the change in the uncertainty over, for example, the Iberian Peninsula is enormous when you factor this in. So this is coming back to the fact that in the forced signal, this is where we see a big drying in the Mediterranean region in the winter, whereas when they get their rain. So yeah, I think this idea of capturing these things that impact the projected changes here are really important to try to capture in our projections. It's really important that we get these things in there. So that's all I wanted to say about that. I think I'm doing okay for time. I think I'm nearly done. So and finally, I just wanted to highlight the UK climate projections UKCP 18 project from the Met Office. And now this is something that the Met Office now produces kind of periodically. There was UKCP 09 and UKCP 18 now. And these are specific tailored climate projections that they produce for the UK government effectively to provide the UK government with climate change information. So which can be used in planning, adaptation, basically feeds into decision makers. And it's a really interesting product. And it incorporates some of these different observational constraints. So they've got their own method, and it's actually phenomenally complicated. So I won't go into it here, and nor probably could I do it justice here. But yeah, I just wanted to highlight this because I think it's a really cool initiative, and it's great that that the Met Office are doing this, and actually that they make their own. They're not just taking, when they do this, they're not just taking CEAT models off the shelf. They're taking them, they're carefully analyzing them, thinking about which are appropriate. They've got, for example, in some of them, they've got several screening steps that go into this, and also they run their own perturbed parameter projections to try to better reflect uncertainty. So this is a really great tool and great project. But just wanted to make the point here that this is kind of now, rather than go from this is kind of an area where climate science has gone from being predicting future changes in the direction of future changes to actually being people being quite precise, and basically there being more demand for actual climate information and projections, right? People want more accurate information, and they want more useful information. So I think this is and this is why things like climate services are now a growing sector in our science. Okay, so yeah, finally, I just want to go through. So just to summarize, the European climate is projected to get warmer and wetter in winter, except for the Mediterranean, which dries, and warmer and drier in summer for most of mainland Europe. The significant uncertainties arise from future emission scenarios, which is the leading order uncertainty, but also uncertainty in the climate response to a given warming or a given emission scenario. There's also significant uncertainty from the large-scale atmospheric circulation response to climate change. So that's something that we don't know well. There's internal variability associated with that, but also the projected signal. I didn't say too much about that actually, but the projected changes in the winds and the jet stream are pretty weak compared to, say, interannual variability. So I think understanding how well we trust these and understanding the model deficiencies that might affect these things is a really important area of our science at the moment going forward to make. And I think it's something which will have a big impact on allowing us to put more trust in our climate projections. I think some of these model deficiencies we see do undermine to some extent some of the projections. And it's an ongoing research challenge to identify and apply useful observational constraints to adjust these climate projections, because of course what we'd really hope for is the perfect model to just run with, finest resolution that we can run, infinite number of ensemble members covering every scenario, works perfectly. We know we don't have that, and we know we're not going to have that on any time scale on which we need to make decisions and provide information to people to make those decisions. So I think this idea of applying observational constraints and making the most out of the climate projections that we have, that come out of the climate models that we have, is going to continue to be an ongoing research challenge and probably becoming more important. And that's it. Thanks.
Great, thank you very much, Chris. Big round of applause from me, and I'm sure from everybody else who's listening in. A fantastic kind of summary there. So if we have any questions for Chris, can you please put them in the Q&A? We have some questions coming in, so I'll come to those in a minute. But first of all, I wanted to introduce Nigel Arnell, who is our responder today, I guess, to give us a context of how this work is applied, whether that's for people in policy or kind of looking at adaptation. So Nigel is a professor of climate system science in the Department of Meteorology at the University of Reading. He's primarily interested in the impacts of climate change, and particularly in how we can use robust climate scenarios to inform decision making on adaptation and resilience. It's previously director of the Walker Institute at the University of Reading and has been involved in almost all of the IPCC assessments and led the peer reviews for the last 2 UK climate change risk assessments. So I'll hand over to you, Nigel, really to put, I guess, all this wonderful science into context.
Right, thanks, Liz, and thanks, Chris, for that really very detailed and very impressive presentation of what some of the big issues are in projecting future climate. We'll have noticed that COP27 has just started, and climate change has got a really high profile at the moment in the media and in politics. A lot of the focus is on mitigation. What do we need to do to reduce emissions, to reduce future consequences, and so on? And climate models have been really central in understanding what we need to do in order to reduce emissions, in order to hit the internationally agreed climate policy targets. They tell us about when we need to hit net zero and so on and so forth. But we also need to adapt, and that's becoming increasingly important, and it'll have quite a high profile, I think, in COP27 over the next couple of weeks. We've experienced big changes in weather in the last few years, and we're clearly going to experience them again in the future. The infrastructure that we rely on is based on our previous understanding of what climate did, maybe Victorian impressions of what climate did. Things have got to change in the UK and elsewhere. So we need to adapt to a changing climate. And of course, the big question is, what do we need to adapt to? Now, we could just sort of make a number up or try and adapt to something extreme. And in many senses, that's the simplest thing to do. But we could then under-adapt or over-adapt. So what we really need to do in order to adapt is have some understanding of what's going to happen to the things that drive pressures on our infrastructure, on our environment, on our resources, and so on over the next whatever time period we're interested in. And this is where the climate models fit in, and where essentially I think the most interesting and exciting uses of climate models is in providing information that helps inform adaptation. So I've already got 4 points I like to make here, following on and building on things that Chris mentioned. The first is that we really do need a robust understanding of how the sorts of aspects of weather that we're concerned about are likely to change. Chris mentioned the 2 sources of uncertainty, the primary one being, well, over the long term, the primary one being what happens to emissions, and the other one being what this climate system does in response to those emissions. And I think Chris described really well a lot of the ways that research is helping us understand how the climate system might respond and how we might come up with better, more robust, more reliable projections of how the system might respond. So that's a big area of science, helping narrow down the uncertainty range. But the uncertainty range is really important. The second key point I want to make, apart from doing the science, is really, really important. Second point is that we need some mechanism to translate it into the sort of information that normal people can use. Chris mentioned UKCP 18. It's a really valuable resource. It takes a lot of the hard work out of interpreting climate model output, dealing with massive data files, all sorts of stuff that makes climate science information pretty unusable in practice. So we'd need this intermediary stage. And UKCP 18 projections are a really good example of that. They have strengths and weaknesses, so you need to understand them. But there's a real scope for this translation process, for linking the science into the practice, making sure that information is presented in ways that are useful and relevant. A third point is that we not only need to have the information, we need to have some sort of guidance or framework or understanding for how we use that information. Chris mentioned the different climate forcings that are used to run the climate models, RCPs and SSPs, and there was some discussion in the chat which says, what are they? And they're frankly rather cryptic devices designed as experimental tools for scientists. But if you were interested in policy, then you don't really want to build a policy around a cryptic experimental design tool. You might want to follow, for example, the Committee on Climate Change guidance, which says plan to adapt to 2, but think about adapting to a 4-degree world. So we need some guidance and some way of interpreting how we use these sort of projections as to what it is we're seeking to adapt to. And that's influenced by our risk aversion, our risk tolerance, and so on. And that in itself poses some challenges about how we interpret the information that we're producing from the climate science perspective, and how to map it onto the sorts of demands and requirements of policymakers or those seeking to adapt or regulate adaptation. There's in my view, a bit of a disconnect between the science community and the user community, and that's something we really need to address. But my fourth point builds on what Chris was showing, which was how, as we've gone through each generation of models, the answers have got slightly different, sometimes quite dramatically different. If you introduce constraints, you get slightly different results. And if you introduce constraints in different ways, you get slightly different results. And as we learn more about how circulation changes, we get refined projections of what might happen. And to me, the big key conclusion of this is that whilst these climate models are really important for when we're seeking to work out what we need to adapt to, we shouldn't rely on them too precisely and too numerically. We shouldn't treat the ensembles of models that we have today as our perfect set of information that we would then go and redesign our infrastructure to. We need to be much more sophisticated about how we use the evidence and the information that's provided by these climate models in order to inform adaptation decisions. And that's a high-level policy. It's about, for example, policy towards retrofitting houses, toward what sort of temperature standards do we want to have? And it's about specifics. It's about how do we redesign a new building that we expect to last for 50 years? What design rules do we use for that? So we need to be very careful about how we use the information from climate models. They're really important, they're central. We can't really make any progress without them, but we shouldn't essentially just treat dealing with climate change as being a question of reformatting the output from a climate model and sticking it into our design calculations. It's way more sophisticated than that, and it's influenced by our risk tolerance and risk aversion and so on and so forth. But I think Chris has presented a really good example of how the science is evolving, it's developing, giving us a really good idea about the sources of uncertainty, the things that we're making that are being improved and narrow down the uncertainty, and how we can use the latest climate science to help, we hope, make informed decisions about how to adapt to what is clearly going to be quite a different climate over the next few decades. Thanks.
Great, thanks, Nigel. Really, I think that really kind of highlights both the power of the science, but I guess some of the issues really in how we kind of apply that. So that's really great. I'm going to pick up on a couple of quick questions that were in the chat, actually. And there was an answer to what does RCP and SSP mean, but I wonder if either of you or both of you would comment on why we've shifted from RCP to SSP. What was the rationale of changing? What extra information is in the SSP that wasn't in the RCPs?
Well, I can have a go at that one. Okay, so it's to do with experimental design. In the very first years when climate models were run, they were run with relatively simple projections of how, or descriptions of how emissions might change. So the first generation of climate models the first generation of transient models would say, let's assume CO2 increases at 1% per year. That's an arbitrary number. It's not far off what was happening at the time, but it's not a projection of what's going to happen. But by running that through, you can get some idea of what the system does in response to that continued forcing. And then in the early 2000s, the idea was that, well, we can be a bit more sophisticated than that, because we can get some idea, if we know how the economy is going to change, how energy use might change, or we can describe by scenarios how the economy might change, then we can map those onto different ideas about what might happen to future emissions. And we can run those through. So some of you, the oldest amongst us, will remember the SRES scenarios, A1, B1, that sort of thing. They basically describe different socioeconomic conditions with high emissions, low emissions, and so on. And for various reasons which would take too long to go into, after a while it was realized that probably wasn't the right way because it got complicated. So the next set of ideas was to say, right, well, let's step back a bit and and be a bit more stylized about the forcings that we're going to use in our consistent experimental design. The reason for being consistent is that it allows us to build these ensembles of models so we can compare. That's really, really important. But we can't, and using the 1% per year increase was a good way of doing that, but it was a bit complicated. It didn't really, given the complexity, it doesn't really help much. So you could say, right, well, let's just have some external forcing that hits a particular level of radiative forcing by the end of the century. For example, 8.5 watts per square meter. Mm-hmm. And then you could define that as a scenario. The complication is that it's not just CO2 that's important, it's methane, it's the aerosols, et cetera, et cetera, et cetera. And you could end up by making lots of arbitrary assumptions about, well, what do you assume about these things? So the compromise was to pick some stories from what were in the literature, essentially from studies that have been done using economic and so on models to say, under this economic world, we will get this pattern of economic development, and therefore these emissions of aerosols, et cetera, et cetera. So the representative concentration pathways were effectively a subset of N. There are hundreds of these plausible stories around at the time, and as a subset of some representative pathways representing high forcings and low forcings and intermediate forcings. So that's what the RCPs were. So they're experimental devices, not projections. And it'd be really to hear the SSP based ones are essentially the same, but they've got different sets of socioeconomic conditions behind them. So they're fundamentally, in principle, the same, but in detail, they're different.
Okay.
But that's where they come from. And that's why they're not projections of what would happen.
Yeah.
This is why there's a disconnect between the sort of discussions that are going on in Sharm el-Sheikh about the effect of commitments made by countries under the United Nations Framework Convention. Those aren't reflected at all in these emission scenarios that are used to drive the big climate models.
Mm.
There's this disconnect, but that's what they are. There was a move to try and give them sort of friendlier names, but that backfired because people would then interpret them as projections. And
Yes.
in my view, the more cryptic the name, the better, because it makes clear they're experimental devices. They're not real things.
Yeah.
Doesn't help with the communications though.
Yeah. So Chris, we had a question from Helen, just for clarification here. So she said, if I understand correctly, CMIP 6 shows stronger summer warming than CMIP 5 and weaker winter warming. Is that right? So CMIP 6 shows stronger summer warming and weaker winter warming than CMIP 5.
No, I think it's maybe that's regionally dependent then. So it's stronger summer warming in all regions, and it's quite similar in winter. Basically, in winter it's quite similar to CMIP 5. Yeah, so that's an interesting thing to note. Yeah, that's I don't exactly know why that is, to be honest with you. I mean, it's quite modest, I would say. I'm looking at the slides now. I'd probably share them so that others can see. I will quickly share that slide again, because it might be useful for others. Yeah, so this was the slide I think that we're talking about over Europe. So I can't see because I've got the thing open, but yeah, so they're quite similar by the end of the century and mid-century in the winter. They are quite similar. I think the clearer signal is in the summer when they're significantly warmer. My guess is that there's potentially some circulation effects that are mediating this, but I don't know off the top of my head exactly why that is. So yeah, I can't help.
Okay, great. And a couple of questions around the constraints, so the latter part of the talk. So one from Clara saying, what's an example of a constraint that you might put on a climate projection when you use observational data to improve? And then one from Bruno, once an observational constraint is well understood, why is the constraint not built into the climate model algorithms to immediately rule out unrealistic scenarios? So can you give us an example of one and why they're not then implemented?
Yeah, so it's useful to actually, both those questions are useful to clarify here, because it should be clear that these are constraints that are applied in post-processing. These simulations all just run, like as Nigel was saying, then they're all run on their own and no one really knows what they're going to do. And the properties you get out, it's important to remember with these things that they're emergent properties to a certain extent anyway. No one's put anything in. They're kind of, we've tried to do our best to, all these places do their best to simulate all the physics as well as they can, and what you get out is the emergent property of the interaction of all these systems and the physics. So the observational constraints that I'm talking about are all applied in a post-processing way, which I think explains why it's not really done to rule out unrealistic scenarios, like Bruno said. Now there is in when people are developing these models and tuning, there is tuning aspects that go on. I don't know all the ins and outs of how different centers do all of that. So there's certainly tuning that goes in, but in terms of the observational constraints that that I was talking about towards the end, in terms of post-processing, they're done at a later stage. So, but there very well may be sensible ways to immediately rule out unrealistic scenarios. And I think probably some centers probably do that to rule out really unrealistic scenarios in their model development. If over the historical period they have enormous warming that they think is completely unrealistic, they probably redo the model and change it. So that's kind of speculation. In terms of an example of a constraint, to answer Clara's question, a really simple one is in terms of the different methods I showed. A really simple one was basically taking a large ensemble of data and comparing it to the observed evolution, and just coming up with a simple least squares fit for each of the models and weighting them. So some of those basically say, well, this model is warming too quickly towards the the later 21st century. Let's give that less weight. Let's give some others that are closer to the observations more weight, and then recompute our ensemble mean and then distribution based on that. And then we see how it does. That's the kind of, so the idea is that there's reasons to think that, you know, perhaps it's naive, I don't know, but there are definitely reasons to think that the ones that capture some of the observed variability best might represent the future climate better. And that's just a simple way that that's done in one example.
Great, thank you. So just focusing back on uncertainties, and I think this goes for both of you. Obviously, it's, as you say, it's about narrowing down the range of uncertainty. And if we just focus on UKCP 18, obviously came out in 2018, and then there's been an update since. I think this year there was the probabilistic output that came. Is this a way of trying to kind of narrow down the uncertainties in the output? Is that one example or not?
Yeah, so I mean, I think I should say I use constraint here, but I probably should say that's sort of a loaded term, because for some of these things it might be that our models are overconfident in certain areas, and I think particularly when they perform. And now again, I'm slightly speaking above my detailed expertise here, but when they produced UKCP 18, they really went out of their way to try to sample some of the uncertainty that was not captured by the actual Met Office model themselves. So they ran the Met Office model, the for different parameter sets, but also found that even then they weren't fully spanning what all of these different couple models got. So actually they then included some of those to try to capture that. So it kind of goes both ways. It's that's why it's such a challenge, I suppose. Like, it's not just about saying, oh, we've got this much uncertainty, we want it to be lower, but you can only do it if it's well justified and reasonable, if you see what I mean. So actually, in terms of uncertainty, I think the UKCP, my impression is that they're actually quite conservative in that sense. They've got quite wide uncertainty, and if you compare it to, say, if you look at it, you'll see that there's quite wide uncertainties in there, and my impression is they're quite conservative in that respect.
Nigel, any thoughts on that?
Yeah, but my view is that the aim shouldn't necessarily be to reduce uncertainty, but to understand it.
Yeah.
Because I think, as Chris mentioned, if all the models are doing the same thing wrong, they'd be consistent, but they'd be wrong. So having the same answer for the wrong reasons isn't going to help. But it's understanding why you've got the uncertainty, and that helps inform making decisions based on different risk appetites. Are you really concerned about the top end extreme, or are you okay with the sort of central estimate? And understanding why there's this uncertainty, why there's range, is really important, because it may be that some dimensions of that uncertainty actually aren't that relevant to the system that you're seeking to adapt. But it's understanding where it comes from, and it's to do. There's a big discussion about where it comes from, but part of it is to do with uncertainty in the way the circulation is changing. So understanding that helps you get some idea of, if things that are relevant based on circulation, then that uncertainty range is important. Whereas some are more to do with climate sensitivity, and therefore the sort of the thermodynamic effect of increasing temperatures. And you can perhaps get a better handle on how reasonable some of the projected changes are. So it's really understanding the uncertainty rather than in itself trying to reduce it, I think, is important. Which may be different to a weather forecast. That might be a separate topic for discussion. The principles are different.
And you said, I think, Nigel, it's translation, it's guidance on this, and UKCP 18 goes part of that way, but there's still a disconnect, I guess. And I suppose, how do we fill that gap?
Well, in my view, one of the ways of filling it is to have dialogue early on with those who are seeking to regulate how we adapt. Committee on Climate Change, for example, the Environment Agency, Scottish Environment Protection Agency, those who have a sort of an interest in saying, what are we seeking to adapt to? And say, so what sort of decisions and assumptions are reasonable? What timescales are people interested in? And then use that to help inform the way information is presented and provided.
And so I guess the guidance or the translation is different for each, say, sector that you might be engaging with, or do you think, could it be an overall set of guidance and then more specific detail depending on timescales and the sector that you're looking at?
Yeah, well, time horizon is a really important one for the sectors that have a really rapid turnover, and I think IT sectors tend to assume they've got a quick turnover. They have the time, what happens at the end of the century is pretty irrelevant. Whereas if we're trying to manage urban drainage, then we would need to worry about that. So I think it's going to be unrealistic to expect a single set of framework guidance for everything, but it might be that there's some overall concept or structure that helps different organizations, different groups think in a consistent way about making adaptation decisions and the information they need, and how to interpret the sort of climate projections that Chris and so on have been talking about.
So, Nigel, without maybe I can jump in. Sorry,
yeah.
Liz, but where do you stand on the kind of trend, I guess, towards thinking about like storylines in some of these approaches? Like, what's your opinion on some of those, Nigel? Because the idea with those, should I say, is to say, rather than say you've got a probabilistic projection of something, is to think about particular storylines of, say, climate change and big impact events and stuff, and try to kind of model and understand those well, which is good in a process way. I just wondered where you stood on those, Nigel, if you thought about them.
I think they're a really, really powerful device, and I think, in my view, they're probably more generally useful than a probabilistic approach for all sorts of reasons that it would take more than 9 minutes to explain. But the point is, it's not one size fits all for all different uses. And I think a storyline type approach where you talk through feasible things that might happen and work out responses to those different sorts of stresses, I think is really, really important. Complemented by a sort of more probabilistic way of looking at what the plausible range might be. So it's not, I think what we need to do in the community is not say, this is the way of going about it, these are the information, you've got to follow this way of doing it. There are lots of different ways of using information related to the nature of the decision that's being made. So I think we need to make sure that we provide information in ways that allows users in a sort of guided and informed way to make sensible decisions.
I should say, just on the storyline thing as well, that I think it's an interesting one as a scientist as well, because an example would be, say, you've got 10 models and 9 are projecting one scenario and 1 is projecting something different. On the face of it, you would think, well, it's the one that 9 is projecting is going to be more likely, but actually it's then on the scientists to then go and understand, well, why is that one doing what it's doing? If it's doing it for all the right reasons and it's plausible, then you then have to add more weight to it. So I think that's the side of it where I think as someone who's we're interested in doing the physical science here, that's where I think we can add the value on those types of conversations, I think. Just around, I know you know that, Nigel, but just to
that's a really important point, is knowing why some models do things differently to the rest, because they may be right, but it's understanding. So understanding is really, really important. Understanding why models are doing the same or different things. But I remember back, I've been involved in this business for sufficiently long that when we started and we had 3 or 4 GCMs to talk about, essentially that was a storyline approach. Having more information is what's caused this explosion and confusion about how we use and interpret information.
Can I ask, I guess, following on from that, and I know there's a focus that you cover, Nigel, in wildfires. So a lot of the output is either temperature or precipitation focused, and obviously wildfires is a combination of these things. So how do we kind of, again, it's a translation of the information, but to a particular kind of area, a particular phenomena. How's that kind of, what step am I missing, I guess, from the climate model output into having some useful projections around, say, wildfires, just as an example?
Well, I'm happy to have a go at that, but essentially the environmental hazards that we're concerned about, all the information that you need to understand those comes out of climate models, with varying degrees of reliability, robustness, etc., etc. So in one sense, it's just a question of reformatting the output and running it through, subject to all the caveats we've been talking about before. So the information's there. I think what we do need to resist, though, is trying to stick into our climate models some of the things that are more dependent on decisions and human reactions and so on. So, for example, putting in a wildfire model in a climate model probably isn't isn't in itself very helpful, because there are so many things that might influence the wildfire that aren't relevant to the climate model. So doing things offline, I think, is really, really important. But I think a lot of the information that we need is there. But I think we should resist the temptation to stick too many things into our weather and climate models, when by doing so, we might have to make rather simplistic assumptions about what it is that causes that hazard or whatever.
Yeah. And just thinking about the regional models and the detail that you get, and I think there was a caveat there that not to take everything completely literally, but Chris, I think there was one slide you had, summer precipitation, and I think it showed increase in precipitation in the north of Europe and a decrease in the south. But Iceland stood out. It was bright red, had a kind of significant decrease. You know, again, is there a logic there? Is the rationale why Iceland is completely different to the rest of Northern Europe, or is that something that, again, there's just we don't understand why, or we can't take that as literal from the climate models?
Well, you've put me on the spot there. I don't know about anything about Iceland. That was a really good spot. I'm gonna have to have a look at that. But yeah, I mean, that's you're right. You'd have to understand why that's the case. I mean, that does seem strange to me. But I don't know, to be honest with you. That would be something where it must be circulation driven, I would guess, because it's not the kind of the aridification of the Mediterranean region, which is I think largely due to the strengthening of the subtropical high in the south. But I don't know. I don't know why.
I guess the overall question is, if we get down to these regional scales, and again, UKCP is a classic example. How much detail is there in the climate models to really get that? And Iceland, I picked on that, but generally, I think once you get down to that really small scale.
Yeah, I think that's fair. The resolution of the models of those scales is not great. What I would say is, I caution. I certainly don't think the answer is in necessarily doing lots of regional modeling. Now, regional modeling is definitely valuable, but for example, if you took these climate model outputs that I've based this on and you perform regional modeling, it would have almost very similar but finer scale detail, but it would have effectively the same response, because it's large scale changes and large scale thermodynamic changes that are driven by the global model that are driving a lot of these changes. So even I think sometimes on the resolution things, people are worried, my town isn't represented in climate models. That a lot of these things are large scale things. So I think those, with your Iceland changes, which I'm going to look at as soon as we've done here, I think that would be the same in whether you did, you need to be careful about the regional details. You need to understand where they're coming from, but also I don't think the answer is just regional modeling, for example. Not that you were suggesting it was, but I think that's where you need to be a bit careful with thinking about these different scales.
Great. Thank you. So I'm conscious of time. I'm going to wrap up there, but a big thank you to both of you for both the presentation, but the discussion, I think, during that Q&A as well. That was excellent. Thank you. And I'm going to hand over to Hilary.
Yes, thank you, Chris, and thank you, Nigel. There's so much information and so much context, which was really useful, and really good to hear about the politics of it all, as well as the science, and bringing them together. I feel as if I've been brought up to date quite well on some climate change issues. And also thanks to the Royal Met Soc for laying on this event so well. We have a topic for the spring masterclass series. These are going to be on extreme summer weather. There's going to be talks on wildfires, heat waves, and droughts and flash floods. One of the speakers is going to be Nigel Arnell, who we've been hearing from today. So that's a good advertisement. Thank you all once again.
Cheers. Thanks, everyone.